Hello everybody, this is Jim Corkins, and we are continuing on with kinematics, or motion, in one dimension. And we're today we're starting with position versus time graphs. Again, if you haven't started the reading, please do so. Those readings will be indicated in Canvas. Alright, so we are going to be studying very closely what position versus time graphs are. We are going to use our knowledge about motion diagrams that we learned last time to help us interpret and create equations using position versus time graph, or in other words, x versus t graphs. Okay, so here are the basics of interpreting position versus time graph. Again, slope is the velocity. Okay, so a steeper slope is a faster speed, a more level slope is a slower speed, a perfectly level slope is 0. Negative slopes means, so that's a negative slope means you're moving to the left. And a positive slope means you're moving to the right. Okay? And so we're going to use those little parts of our understanding of position versus time graphs, or x versus t graphs, to understand and create equations. Okay. Now, part of that is this. We are going to be dealing with constant velocity. So it's going to be kind of weird because there's still going to be instantaneous velocities that we learned last time. And those are those velocities at an instant in time, a fraction of a second in time. And so that'll be an instant in time. But since these are going to be straight lines, it's going to be kind of hard to distinguish them, but I will try to point them out. What the instantaneous velocities are at like 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. Okay? So here is basically what we're going to do. Okay? So suppose you had a car and you measured it in kilometers per hour, and that car drove for a period of 3 hours, and it drove a total distance of 150 kilometers. Okay, so your starting position would be 0 kilometers. Your ending position would be 150 kilometers, or positive 150 kilometers. Your period of time, actually, that should be a positive there. We'll just put a little positive right there. A little positive 150 kilometers. The total period of time that you were driving was 3 hours. And if you take what we learned last time, that velocity is displacement over time, and that displacement is final position minus beginning position over that t final minus t initial. This is going to be a positive 150 kilometers minus 0 kilometers displacement over 3 hours minus 0 hours. So that's going to be a total velocity, total average velocity of the entire trip of a positive 150 kilometers over the period of 3 hours. Okay, and that's how we got that. What that would look like at a number line. So this data, if you drove 50 kilometers in 1 hour, and that was your displacement over time. And then the next hour you drove another 50 kilometers in the next hour, and then the last hour you drove another 50 kilometers. Your velocities at each one of these points in time will be 50 kilometers per hour. Again, these are our instantaneous velocities at this time. So right here we have a position in the x direction versus time. So these are positive positions. So you're moving to the right 50 kilometers, 100 kilometers, 150 kilometers, 200 kilometers. This is our time, 0 seconds, 0 hours, I should say. 1 hour, 2 hours, 3 hours, 4 hours. Okay. Now, your total trip, again, you started here at the 0 hour mark. You ended at the 3 hour mark. 0 hour to 3 hour. So the total trip again was positive 150 kilometer displacement over the period of 3 hours. Now, at these points right here at the 1 hour mark, you were driving and with that instantaneous velocity 30 kilometers for that period of 1 hour. Okay. At the next hour, you're driving 50 kilometers over that hour. And finally, at that third hour, you're driving another 150 kilometers per hour. So, slope in a position versus time graph represents velocity. So we started out at 0 seconds. We ended 0 kilometers. We ended at a positive 150 kilometers. And it took you 3 hours to do that. Okay? So the total slope of this is going to be, which represents the end position minus beginning position, is going to be a positive 150 kilometers over the period of 3 hours. And if you reduce it, that'll be 50 kilometers, positive 50 kilometers displacement for every hour. Now, the instantaneous velocity right here, and I'll mark it in red, is across this point right here. And this pertains to this guy. That is this guy's slope, which is positive 50 kilometers for 1 hour. The next slope that we have, and we'll use purple, is this guy. So at this point, this is this instantaneous velocity. So that's the velocity at that instant of the 2 hour mark, which again is also another positive 50 kilometers over the period of 1 hour, over the next hour. And then finally, this last guy, you have another instantaneous velocity, which is this guy, which is another positive 50 kilometers over the period of 1 hour. As long as all of these slopes are the same, this overall is going to be a straight line. So the average velocity, if you reduce it, is going to become each one of those instantaneous velocities. Okay, so this is the basics of a position versus time graph. And this is a positive slope. A positive slope would look like something like this. So a positive slope would look like that. So I'm going to write a position versus time graph. Actually, I'm going to do this over here. So if we write a position versus time graph right here, this is double positive x, so really far, close to the left, and like 2 steps, really far to the left. Okay? So if you were moving really fast, which I'll use red, to the right, you would have a positive velocity over this period of time t. So over this period of time t. So in other words, this slope would be really, really positive. So that is a steep slope over that period of time t. If it's not moving so fast, notice that this slope is a little bit more level. So it's not, in fact, this is twice, the red is twice as steep as the blue. for negative slopes over here, notice this slope right here, which I gotta be a little bit slower. Notice that this negative slope, which is a negative slope, it actually is the same slope as this. It's the same steepness. So they both have the same speed, but one's moving to the right, one's moving to the left. And this green guy right here is, again, this is slope. The steepness of this is the same steepness of the other green one, but they're just different directions. This is moving to the left, this is moving to the right. So that's all the different types. That's how steep and level and how they're related to speed, and I created those dots from position. Right here, you started, this one's started here and it ended here at this time. Okay, so quick little review. Let's try something practical. This will make more sense, I think. Okay, so here's what I want to do. Here is a position versus time graph. These are positive positions by 1. So starting at 0, 1, positive 1, positive 2, positive 3, positive 4, positive 5. To the left would be negative 1, negative 2, negative 3, negative 4, negative 5. And this time period is over a period of 4 seconds. Okay, so what you're being asked to do is interpret this position versus time graph and create a motion diagram below. You're also being asked to fill in these variables. What's your final position? What's your initial position? What is your overall period of time? And what is your velocity over this entire graph? And from there, we're going to create an equation that will predict, this will be like y is equal to mx plus b. We'll talk about that in a second. But this is a linear fit for this graph. Okay, so let's do this together. All right. So it looks like at the 0-second mark, it starts out here at 0 meters. So this is the initial position. And it looks like it gets to a position of positive 5 meters at the 4-second mark. So it started here, you go with time, it ended right here, that's the arrow of time, and that's also the displacement. The displacement is going to be positive 5 meters minus 0 meters over the period of 4 seconds. So in other words, you started here and you ended at 1, 2, 3, 4, 5 meters to the right. So the velocity of this is positive 5 meters over the period of 4 seconds. So that is our motion diagram for this. Okay, we could have done all the little times, 0 to 1, 0 to 2, 1 to 2, 2 to 3, 3 to 4. But right now we just want to do whatever this is ending at. So we're just going to do the total trip. Since this is a straight line, when we reduce it, we would get all those instantaneous velocities. Okay, let's fill in the variables. Your end position is positive 5. Your beginning position is 0 meters. The period of time is 4 seconds. And the total velocity is what we indicated is going to be positive 5 meters over the period of 4 seconds. Oops. You need to write that seconds. It's already indicated right there. All right. Now, for the linear fit, you've probably learned in mathematics y is equal to mx plus b. Y is going to be the vertical axis. In this case, the vertical axis is the horizontal positions, which is, weirdly, it's x. The x here is time, t. So this x-axis is time. The vertical axis is horizontal positions. Now, your starting position, your y-intercept, that has always been weird for me, that's just where your line crosses the vertical axis. It's also, in physics, it's your initial position. Okay? And m is the slope. That would be rise over run. But since we have units to it, rise is going to be meters, run is going to be in seconds. So this is actually going to be a velocity. And what we're trying to do with this equation is predict any final position that we want, given a velocity, a period of time, and a starting position. So that's how you take a specified linear fit and turn it into something that's specific for our circumstance. So that is what you're asked to do right here. We're trying to predict any position. Our velocity is going to be positive 5 meters displacement over the period of 4 seconds. We don't have to reduce for any period of time. And our starting position is 0 meters. I'm going to keep, you could just have positive 5 meters over 4 seconds delta t and leave this blank. But I prefer to put this in here because that tells me that it's absolutely starting at the 0 meter mark. The more information you have, the better off you're going to be. So let's see if this works. So what we're going to do is try to predict the final position at 4 seconds. Because if we put in 4 seconds for time, we should end up with positive 5. So let's do it. So positive 5 meters over the period of 4 seconds. Delta t is going to be 4 seconds. And starting out at a position of 0 meters. 4 seconds is going to cancel out with this. So this is positive 5 meters plus 0 meters, which is going to be positive 5 meters. So it works. We could also predict anywhere it's going to be. So this linear fit seems accurate. Let's see where it's going to be at the, at the 8-second mark. Well, positive 5 meters over the period of 4 seconds times 8 seconds plus 0. This is going to cancel out with this. This will be a 2. So this is going to be positive 5 times 2 plus 0 is going to be positive 10 meters, which makes sense. In 4 seconds, it ends up at positive 5 meter position. In another 4 seconds, it should be at a positive 10 meter position. Okay. So this is what I want to do. I want to use your concepts of motion diagrams, use your concepts of linear fits on any position versus time graph, and I want you to fill in these variables based off of what you see on the graph, but also your motion diagram, and create a linear equation that looks just like this. One that could tell us given any period of time what your position should be. Let's try a different one, and I want you to try this one on your own. And what we'll do is I want you to try it on your own, and then we'll do this together, and then I want you to answer the question here too. You're not only supposed to create an equation, but you're supposed to tell me what the position will be at the 10-second mark. Okay, so you have a position versus time graph here. Here's all the positions, and this is over the period of 4 seconds, the same graph that we just did. It's just a different line. So go ahead and fill out the motion diagram, these variables, create a predictive equation, and then plug in 10 seconds for the time frame, delta t, and find out what your position should be at the 10-second mark. So try this on your own. Go ahead and pause the video now. Okay. Cool. So starting here at the 0-second mark, if you bring this up, the y-intercept, or it looks like its starting position, is +5. So it looks like it started out here at the +5. So the +5 meters is our starting position, and that happened at 0 seconds. It looks like it ends up at the 0 meter mark at 4 seconds. So this is the end position after 4 seconds. So that looks like 0. And the period time is 4 seconds. So you started here, and after 4 seconds, you're here. That means starting here at the +5, you went to the left 1, 2, 3, 4, 5. So you went 5 steps to the left. In other words, your end position minus your +5 meter starting position. So that displacement is going to be -5 over the period of 4 seconds. So -5 over the period of 4 seconds. Don't need to put the S there. All right. Well, predicting any position, the slope is going to be -5 meters displacement over the period of 4 seconds times delta t. That's our horizontal axis. This is our vertical axis. And our starting position was +5 meters. Okay. Now, if we put 4 seconds in here, 4 seconds divided by 4 seconds is 1. -5 meters plus 5 meters is 0. So this is predictive. This does fit the data that's on the graph. Now, the problem is asking, put in 10 seconds. So -5 meters displacement over the period of 4 seconds times 10 seconds plus 5 meters. Okay, so that's going to be 4, so that's going to be 50 divided by 4. I can't do math in my head. So 50 divided by 4, that is the slope. Okay. 5 meters, so that's -12. So plus, let's try that again. 5, that's going to be negative times 10. So that's -50 divided by 4. That is this, so that's -12.5 plus 5 equals -7.5. So our end position should be -7.5. So again, this is -12.5 meters plus 5 meters. And if you continue this line on down, it does kind of look like it's going to continue to that, right? So 10 seconds is very far. So it'll be at the -5 meters at the 8-second mark, and then for another 2 seconds, it's going to go another 2.5 meters. So there you go. Okay. Some of these example problems can get a little bit more complicated. Okay. What happens if you cross from positive positions to negative positions? Okay. So this one you're going to have to think a little bit, but I want you to try the same thing. I want you to fill out the motion diagram. I want you to fill out the end position, the beginning position, the total period of time, which is 4 seconds, and the velocity, or the slope of this line. And then I want you to create a predictive equation, and I want you to figure out at what time this crosses the 0 meter mark. It looks like it's pretty close to 3, but it doesn't look like it's going to be actually at 3. It might be something a little bit before 3. So let's see if you can answer this question right here. All right, so I want you to go ahead and try all this out and then pause the video. Please pause now. Okay, here we go. So it looks like at the 0 second mark, it starts out at positive 4 meters. So positive 4 meters is 0 seconds. So I'm going to put positive 4 meters position. And at the 4 second mark, which is our time, it looks like it ends here at the negative 2 meters. So we're going to put 4 seconds there. And that's negative 2 meters. In other words, it starts at positive 4 meters and ends at negative 2 meters. So it looks like it had a total displacement. It started here and it went 1, 2, 3, 4, 5, 6. It looks like it went, so this is negative 2 minus a positive 4, so negative 2 minus 4, negative 6 meter displacement over that period of 4 seconds. That would reduce down to negative 3 meters over 2 seconds, or negative 0.667 meters for every 1 second, if you want to figure out what the instantaneous slope is at for each second. So this is 4 seconds. This is going to be negative 6 divided by 4. Cool, 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 cool. All right, now for this question. At what time does it cross the 0 meter? At what position was it at 0? At what time was it at 0 meters? So this all starts with our equation. So let's do our equation first. The slope is negative 6 divided by 4. That's 6 meters. Displacement divided by 4 seconds. Delta t. And our starting position is going to be positive 4 meters. So that is our y-intercept. Okay, we want to know at what time it crosses the 0 meters. So I think what they're asking is when are we crossing the 0 meter axis? In other words, if our final position is 0 meters, at what time does it do that? So I think we have to solve for delta t here. Going to have to do a little bit of algebra. That's okay. Okay, here we go. We have to take this positive 4 meters onto the other side. So that means we need to subtract both sides by negative 4 meters. So we're going to subtract both sides by negative 4 meters. So if we do that, that's going to cancel it from that side, and all we're going to have left over is negative 6 meters per 4 seconds, delta t, and 0 meters minus negative 4 plus 0 meters is just negative 4 meters. Okay, so now we have delta t multiplied by negative 6 meters over 4 seconds. So what we have to do now is multiply both sides. So we're going to multiply both sides by 4 seconds because we have to get that 4 seconds onto the other side. Okay, and when we do that, we're going to have negative 16 meter seconds. I know that looks weird. Meters times seconds. So meters times seconds. So put a little dot, meters times seconds. And that's going to be equal to negative 6 meters delta t times delta t. Well, you have 4 was on the denominator. To get it, so that's 1/4. We had to multiply both sides to get it on the other side. Here, this is on the numerator, so we have to divide both sides or multiply both sides by 1 over negative 6 meters. So we're going to do that. So we're going to multiply both sides by 1 over negative 6 meters, or in other words, divide both sides by negative 6 meters, which is going to give us negative 16 meters times seconds over negative 6 meters, and that is going to be equal to delta t. Okay, so negative over negative is a positive. The meters is going to cancel out. The time is going to cancel out. So what we're going to be left with is 16 divided by 6 seconds. And so that will be its actual position. So let's try this again. 16 divided by 6 equals 2.67. So it wasn't at 3, it was just before that. So it was at a position, it was at a position of 0 meters at 2.67 seconds. Okay, I think this is our last thing for this video. And this is what you do when you have multiple lines connected together. Okay, so what do you do when you have multiple lines connected together? So what this is saying is it's kind of telling us a story. Okay, so it looks like it starts here at the positive 10 meter mark at 0 seconds, and then it's traveling to the negative 20 meter mark over the period, which looks like 30 seconds. Okay, and then right here it's got a horizontal line, that means no slope, and so it looks like it's not moving for the period of 10 seconds, right, from 30 seconds to 40 seconds. And then something happens, and starting at negative 20 meters, it ends at the 0 meter mark over the next 40 seconds. Okay, so whenever I look at a graph, I try to interpret it right away. And as you can see, this slope, which is really steep, is going to be faster than this. So it's negative, but see how that's more steep than this other one? So it looks like this is going to be very fast. This is going to be a little bit slower, and this is going to be not at all. So let's see if we can do this. Okay, let's see if we can interpret this. So it looks like its starting position so we're supposed to create equations just like we did here for each one of these lines. There looks like there's the 0 to 30 second line, and then 30 seconds to 40 seconds, and then 40 seconds to 80 seconds. So we're going to create these little predictive equations. Okay? All right. So this first line, it starts out at the positive 10 meter mark. And now it ends at the negative 20 meter mark. So if we figure out, we start here and we're going 1, 2, 3. So that looks like a negative 30 meters over the period of 30 seconds. Okay, and let me try this real quick. Let's see if I could grab a number line. Okay, I'm going to pause this for a second. I'm going to grab a number line. I'll be right back. Okay, and I'm back. I grabbed a number line, and hold on a second. I got to renumber it. I should have grabbed a number line that doesn't have any numbers on it, so I'm going to delete this, and I'll be right back. And I'm back. Okay. So here we go. We have our number line, and I've numbered it. And what I'm going to do is I'm going to make this line red, and I'm going to make this part green so we know what we're talking about. Oops. Make this green. Try that again. Last time is the charm. And I'm going to make the equations colors match that. So again, here we go. We're going to start off with blue. blue. It starts off at the positive 10 meter mark at 0 seconds, and I probably should make sure I got enough room. So at 0 seconds, and it ends over at the negative 20 meter mark at 30 seconds. So this line is really long, and I'm trying not to make a mistake. So it took 5, 10, 15, 20, 25, 30. So it has a velocity of negative 30 meters over the period of 30 seconds. Barely read that. Okay. So this blue line right here started off at positive 10. So positive 10 is the initial position. Its slope is negative 30 meters over the period of 30 seconds, delta t. Ran out of room. And that is the prediction, this linear prediction for just the blue line. Okay, for just the blue line. Okay, the red guy, right here, it starts at negative 20, and it ends at negative 20 over the period of 30 seconds. Of 10 seconds. So in other words, it started here, it ended here, right? So its starting position is negative 20 meters. Its end position is negative 20 meters. When this happens, the only way you could draw this over 10 seconds. It did not move. Okay, so that is 0 meters displacement over that 10 seconds from 30 to 40. Okay, delta t. So this linear fit is only good for this line right there. Now from 40 to 80 seconds, we're going to use green. Now, you started here at 40 seconds, and at 80 seconds, you ended at the 0 meter mark. So, you went all the way over to here. So your displacement is going to be 5, 10, 15, 20. So that's going to be a positive 20 meter displacement over that period. And now it started at 40 seconds to 80 seconds. So that seems like it's going to be over the last 40 seconds. So this is 80 seconds. So 40 seconds, 80 seconds. There you go. So this linear fit is going to look like this. Positive 20 meters over that period displacement of over that period of 40 seconds, delta t, and it started at the negative 20 meter mark. Okay, so that's how you kind of tell a story with position versus time graphs. You could tell a continuous story. You'll also notice that this y-intercept, this is not y, that red line is not y-intercept. If you start here at positive 10 and you end here, this should be your new initial position. And then, since you didn't move, the final position of this for that 10 seconds, because 10 seconds divided by 10 seconds plus 0, 0 minus 20 is negative 20. That final position here is your new starting position over here. So this is the starting position, It ended at -20. That'll make your new initial position. And this ended also at -20, which is your new initial position. And this is at 0. Now, what is your displacement over the 80 seconds? Okay. What is the displacement over the 80 seconds? So this is what we're going to use for our black line. Well, for that 80 seconds displacement, at 0 seconds, you started here. So, and your end position, so you started here, but your end position is, whoop, hold on, I'm sorry, that should be +10. Your starting position is +10 at the 0 second mark. And your end position for the entire trip is at 0. And that's at the 80 second mark. So your overall trip, you started here, you ended here, which is going to be 510. So it's going to be -10 meters over that period of 80 seconds. So overall, what this is saying, you started here, you went to here, you started at the +10, you went to -20, and from -20, you ended at 0. So if you add all those displacements up, that is your average displacement. So your displacement is going to be -10 meters. But your distance traveled is different, right? That's the sum of, that's your total trip that you took. So if we count just steps, don't care about positive or negative, here's how many steps you took. 5, 10, 15, 20, 25, 30, and then you waited for 10 seconds. 35, 40, 45, 50, 55, 60. So you traveled a total distance of 60 meters, right? Because this is, what is it, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Oh, did I miscount? Let's see. Okay, so 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Actually, the distance traveled is 50, right? So you just got to count your steps, right? However, so your average velocity then for the whole trip is right there. It's going to be -10 meters over the period of 80 seconds. But your speed, which is distance traveled over that period of time, is going to be 50 meters distance traveled over the period of 80 seconds. So this is how to read position versus time graphs, and how to pull out meaningful information from that to build motion diagrams. So I'll go over here to build motion diagrams, pull out that meaningful information, and create a regression equation, which is linear, that'll be predictive for anywhere along that line. Okay? And you could then use that information to solve for problems. So this is really powerful stuff. Okay? And I want to teach you to use all of these things. Not if you read something, you could create a position versus time graph. You could create a motion diagram. You'll be given variables, and they usually ask you for something. But I want you to learn all of these tools, all three of these tools. Position versus time graphs, motion diagrams, and creating equations from those. Okay? All right. Thank you very much. I hope you had a good time.